Hey everybody, I'm Andrew Kramer, and I'd like to introduce a new dataset for 3D state estimation and mapping, the ColoRadar dataset from the Autonomous Robotics and Perception Group at the University of Colorado, Boulder. As its name suggests, our dataset is intended to facilitate the use of radar as a primary sensor for research in 3D state estimation and mapping. Now, there are a couple of other publicly available datasets that include radar data, most notably the Oxford Radar Robot Car dataset. But Radar Robot Car has some crucial limitations that are addressed by our dataset. First, like the other currently available radar robotics datasets, Radar Robot Car is autonomous driving focused. This means its vehicle's movement is mostly constrained to the 2D plane. Second, it uses a NavTech radar sensor. Now, the NavTech sensor produces these beautiful high-resolution radar images representing horizontal scans of the environment. These are excellent for some purposes, like autonomous driving, but they aren't really that useful for 3D state estimation or mapping. Lastly, the NavTech sensor weighs 6 kilograms and draws 24 watts, making it pretty unsuitable for small, agile platforms. The ColoRadar dataset, by contrast, uses two small, lightweight radar sensors which fit easily onto our hand-carried sensor rig, shown here. The first is the AWR 1843 radar on a chip from Texas Instruments, and the second is the cascaded imaging radar sensor, also from TI. These radar sensors provide 3D measurements, which makes them suitable for state estimation and mapping in 3D environments. The principal difference between the AWR 1843 and the cascaded sensor is the cascaded sensor has vastly improved angular resolution over the 1843 at the expense of a higher data rate and power draw. The sensor rig also includes an Ouster 64-beam LiDAR sensor and a microstrain IMU. The sensor rig provides synchronized measurements from all four sensors as it undergoes motion with 6 degrees of freedom in a diverse set of 3D environments. Additionally, we provide ground truth poses computed after the fact using global optimization of a LiDAR inertial pose graph. Here we provide short examples from our dataset in various environments. We start in an indoor built environment, the University of Colorado's Engineering Center. Here we can see points from the LiDAR sensor in white, and images from the cascaded radar sensor are represented as a two-dimensional heat map, where red represents lower intensity readings and violet represents higher intensity readings. We should note that while the heat maps in the dataset are three-dimensional, they're collapsed to 2 dimensions in this visualization for ease of interpretation. Now we can see that intensity peaks in the radar images clearly correspond to features of the environment. Crucially, these intensity peaks are repeatable over changes in the sensor rig's pose, meaning they could be tracked to estimate the pose of the sensor rig. We can also see here that the sensor is capable of resolving multiple closely spaced features in the environment. For instance, these aluminum window frames are clearly resolved with separate peaks in the radar image. Now, our second example is an outdoor multi-use path. For this environment, the sensor rig is carried on an electric skateboard, providing speeds of up to 7 meters per second. In this outdoor environment, the sensor is able to clearly detect static obstacles like trees and fences, and also dynamic obstacles like cyclists and pedestrians, as we can see here. I'd also like to highlight another advantage of the ColoRadar dataset over existing radar datasets. We include the raw data streams from our radar sensors. Now, existing radar datasets use the signal processing and target detection methods implemented on board their sensors. These methods are usually designed specifically for applications like advanced driver assistance and are ill-adapted for robotics work as a result. Our dataset provides raw, unprocessed ADC samples and dense 3D radar images for each radar measurement. This gives users the flexibility to experiment with new signal processing methods or to use our pre-processed radar images. Our last example is in a subterranean environment, a former gold and silver mine that now serves as an educational facility for the Colorado School of Mines. We can see that the rock walls of the mine are clearly resolved in the radar images, providing a good reference for odometry. Additionally, other obstacles like vehicles and equipment are clearly visible as well. That's all for now. If you want more detail on our dataset, you can find our paper on archive at this address. You can also download the dataset and associated development tools at arpg.colorado.edu/ColoRadar. Thanks so much for watching.